Welcome everyone, and thank you for being here, and thank you for the organisers for letting me speak. My talk today is going to be on making a Game Boy emulator in Ruby, but yesterday I was thinking it's not exactly what this talk is really about. It's about how the Game Boy works, slash how I wrote an emulator, and this is how it works. Hashtag, oh god, what did I get myself into? My name is Colby Swandale. You can find me on Twitter at oxcolby. If you have any questions, don't be afraid to find me in the hallways afterwards or PM me on Twitter. I have DMs open to the public. So yeah, I made a Game Boy emulator. I'm going to show it to you as the very first thing. So let's give Zelda a shot. So this is Legend of Zelda. It looks like it works, but it's actually not. There's supposed to be a ship, and there's supposed to be lightning, none of which are there. None of which show up. But yeah, it's written in Ruby. There is one tiny C interface into a library called SDL, which is how I'm rendering the script. Oh, there's a lightning. Okay, it works. Maybe. Let's try something else. Let's show Super Mario. This one I like to think works, but as you'll see in a second, it doesn't. So Mario can jump. Yep. And you'll notice that the background won't even scroll. You'll notice that the background will scroll incredibly slowly, slash not at all. But the Goomba works. But the one game that does work, which I am pretty happy about, is Tetris. So this takes a bit of a while to boot up, but I'll fill you in on some of the details. I started this project late in 2015. It took about 7 months to complete. A lot of it was just reading about how the Game Boy works, started implementing some of the components that make it up, and then eventually just went full straight ahead and made the whole thing. And then I gave a talk at RubyConf last year about this emulator as well. If you've seen this talk before, this is going to be slightly different. I've added a lot of new slides. I've also updated a lot of the existing ones. So if you've seen this talk before, don't be afraid to. Bit up a bit more? Okay, sorry. Is that bad? Okay, sorry. So this is Tetris. It's still slow. Unfortunately, this emulator is really unoptimized, but yeah, I can't really do anything against that. I'm not going to show you it all just due to time constraints, but yeah, you can play it if you're patient enough. So yeah, so that's the emulator. So this is the Game Boy here, which, oh, that's meant to be a GIF. Oh, was it showing it? There you go. So this is Game Boy. Actually, no, it's not. This is BMO from a show called Adventure Time. But this is the Game Boy here. It was made by Nintendo in Japan in 1989. It went on to sell 118 million units. Those figures do include the later models, such as the Game Boy Color. Had over 1,000 games, including Tetris, Super Mario Land, Pokemon Red and Blue. And it had a 15-hour battery life, which was pretty huge back for when this was released. Other such competitive devices would only last for about 8 hours or so. So to anyone who is unfamiliar with what an emulator is, Wikipedia defines it basically as a piece of hardware or software known as a host that imitates another piece of hardware or software known as a guest. If you've heard of the term hosting guest before, you're probably familiar with a piece of software called virtual machines. Software like VirtualBox, VMware, Zen, KVM emulate a number of different systems such as like RAM, CPU architectures, disks, and alike. So you've probably used an emulator before. I like to think of it like Inception. Emulators let you run things like operating systems within operating systems if you want to go that far. So if I had a sound, I wouldn't be playing that boom sound right now though. This talk is going to be talking about 4 of the major components that make up the Game Boy. I'm not going to have enough time to break everything down, but these are the main things that make up the Game Boy and how it works. I'm going to be talking about how they work independently, but also how they kind of work together to let you run games and let you play play games like Pokemon Red and Blue and such. So the first thing I'm going to talk about is the CPU. It's the most critical component in the Game Boy. It's the component that will actually read the program, execute all the instructions. It's also known as the main integrated circuit. There's a lot of things that make up the Game Boy, things like registers, instructions, timers, halts, but today I'm only going to be talking about 2 different things. One is registers and the other one are instructions. The CPU in the Game Boy is a Sharp LR35902, that's a mouthful. It's clocked at 4.19 megahertz. It's an 8-bit CPU. It has a 16-bit memory bus, so if you want to read something from an address, you have to use 2 bytes. And it's very similar to another kind of CPU called the Zlog Z80 and the Intel 8080 processors, if anyone is familiar with those. So the main thing I'm going to be talking about is registers and instructions. So registers in the Game Boy are sort of like bits of memory, but they physically sit inside the CPU. They're very quick. There's a very limited number of them. The Game Boy has 10 registers. It has 8 1-byte registers and 2 2-byte registers. Some are available for general use. Others have several particular functions. The A register, and the other thing is they have an identifier on them. So from like AF, BC, SP, and PC. But the A register, for example, is what's known as an accumulator register. It's a general purpose register, but it does something pretty special as well. Certain types of operations will use the A register as a second operand and also store the result of mathematical operations, such as addition and subtraction. The F register is what's known as a status bit register. It holds the status bits of the CPU. So if you want to see like states in the CPU, such as like if the last instruction was a subtraction, if the last instruction resulted in a 0 or a full carry or a half carry. The PC register, or also known as the program counter register, holds the address of the last instruction, of the next instruction to be executed by the CPU. The SP register, or the stack pointer register, holds the address of the top item in the stack. To anyone who is unfamiliar with what a stack is, it's a small region of memory that is mainly used in the Game Boy to pass arguments to subroutines and to also hold the program counter register when the program jumps into a subroutine. Finally, each of the 1-byte registers can be paired together with another 1-byte register, forming a single 2-byte register. These pairings are typically used to reference something in memory. So as you see, like register A and register F have come together to form register AF. And if I manipulate the data in either register A or register F, that will also be reflected in the register AF. So they kind of combine together. So the first thing I started doing when I built this emulator was creating a class to represent our CPU. This class will just encapsulate things like registers and the instructions. And to emulate registers in the CPU, I'm just going to create an instance variable for each register with the same name. And then in the instructions, as you'll see in a few slides, we just use these instance variables to manipulate the data in these emulated registers. So the next important thing about the CPU are the instructions. So these are the actual operations that the CPU will perform. Things like mathematical arithmetic, such as like addition, subtraction, and rotating bits. The Game Boy has 256 instructions. This is a very small subset. A lot of the other instructions are just slight variations of the ones you see on screen that will use like different registers and such. You got instructions like loading data in between registers, performing mathematical operations such as addition, subtraction, bitwise operations such as AND, XOR, and OR, rotating bits, decrementing and incrementing values in registers, pushing items on top of the stack, calling subroutines, no operations, so literally the CPU does nothing for that instruction, loading a piece of data from memory into a register, loading a value from a register into memory, taking an item off the top of the stack, enabling interrupts, and halting the CPU. So these set of instructions come together to form what is known as an opcode table. The table is embedded in a CPU, and it maps the instruction mnemonic, so like LD, A, B, into what's called an opcode. So each instruction has a unique opcode, and when I want the CPU to execute an instruction, I supply the opcode, not the mnemonic. And then that is interpreted by the CPU and then executed. So if we take an example instruction such as enabling interrupts, the opcode for this will be hexadecimal 32. So you read it down the table and then from the left to the right. And then when we compile a program that uses this instruction, that is encoded into binary format. And then that is what is read by the CPU, and that is how it executes that instruction. So it'll read that piece of data, that 8 bits, and then that will map in the circuitry to that instruction that is then performed. So to emulate the opcode table, I just use an array. Each item in the array is the mnemonic of that instruction, and then each instruction is positioned in the array to give me the value of that opcode. So like the opcode for no op is 00, so it's the first item in the array. Some example instructions, like here's LD B, C. So this is loading the value of the C register into the B register. This is very simple, nothing much else than just assigning variable data to each other. Here is increment B, so we're incrementing the value of the B register by 1. And then notice on the second line that we're doing an AND operation on the result of that increment. This is because we're using Ruby. Ruby does not have an 8-bit data type like languages such as C. So that means that values can go up to very big numbers. But in the Game Boy, it's an 8-bit CPU, so it can only handle values up to 8 bits, which is 255. So when you reach the value of 255, you have to flip it back to 0, which is the natural behavior of 8 bits. And if you actually look at this code on GitHub, you'll see that like the result ampersand 0 hexadecimal FF littered all throughout the code. So once we have registers and instructions ready to execute our program, we need a way to execute more than a single instruction. Computers employ what's called fetch and execute. And this works the same way today, but it's much more complex. But the way the Game Boy works is that it will read an instruction from memory using the program counter register, and then it will interpret that instruction and then execute it. And then that repeats forever. So it will just read the instruction, interpret, execute, read the instruction, interpret, execute. It will do that from from when it's first turned on until it pretty much powers off. There are exceptions to that. There's instructions like the halt and the stop instruction, which will actually stop that process from happening, but I won't go into detail for that. To implement this process, it's not difficult at all. We simply reread the instruction from memory. So the MMU variable is the memory, and we're just reading a single byte using the program counter register. We then increment the program counter register by 1, so that we actually go through the code. So the program counter register will tell the CPU what it needs to read. So we got to shift it down every time we use the program counter register. And then using that opcode, we then actually look up the mnemonic of that instruction, and then we just execute it. And then the CPU will actually implement each of those instructions. The last thing about the CPU is that each instruction takes a particular amount of time to complete. Instructions like no op take what's called cycles. Sorry, no op will complete what is called 4 cycles. Sorry. So a cycle is that process I was talking about before, where it reads the instruction from memory and then executes it. So no op takes 4 cycles, but then complex instructions like calling a subroutine takes 16 cycles. And then you'll see other bits of hardware, such as the picture processing unit, take those cycles and use it as well. So to implement this timing, I just have another array that defines the timing for each instruction. And then just using that opcode, then I can just use that as a lookup index as well. And then we assign that to just an instance variable that then can be read by other components in the Game Boy. So the next component is memory. So memory is pretty much long-term storage in the Game Boy world. It's where the program lives, it's where video memory lives, and a few other things. The memory is controlled by what's called the memory management unit. So in the Game Boy, there's not like a stick of RAM that you see in typical computers today. Memory is spread out across different chips that are managed by different components. But the memory management unit is pretty much like the interface to the memory architecture. And so that just lets you, like read the memory without having to worry about like which chip am I reading it from. The Game Boy has 64 kilobytes of memory storage. It has an address space of 65,000 unique addresses, and it's spread across multiple chips. Yep. So the memory is split up into different areas with different purposes. The first half is the game program, so this is where the actual game lives in memory. Then you got video RAM, so that's actually video that's going to get rendered onto the actual screen. Then general RAM, which can be used freely by the program, there's no special purpose for it. And then there's bits at the end reserved for like I/O, hardware RAM, and as you'll see later on, the sprites live in there as well. To emulate memory, we will create a class to represent the memory management unit. It will actually hold all the memory inside itself as well. But you'll see later on that like I actually don't use all of it, but we'll just define it as the full amount because it's a lot easier than having to worry about being smart about it. Here we're going to implement the reading from memory. So this implements the different regions that I was talking about before. So if you're reading from like hexadecimal 0 to hexadecimal 8000, that's going to read from the game cartridge. I haven't implemented it here yet, but in a few slides I'll talk about that. But then if you're reading from like hexadecimal 8000 to hexadecimal 8000, you're reading from video memory, which is stored in that array that we created. And then writing to RAM works exactly the same way, except we're just assigning a value now rather than reading it. And then finally, we create a global variable for the memory management unit. Passing memory around in the Game Boy without things like pointers or references is incredibly difficult, and it's kind of just a lot easier just to define as a global variable rather than having to worry about like the actual state of the RAM. So yeah. So just like the CPU, the memory has registers, but they're kind of different in a particular way. So if you look at the instructions for the CPU, you would notice that there are no instructions to interact with other hardware. Those have been purposely removed, and instead, all the hardware communicates through memory. So you have what's called memory registers, which are particular addresses in memory that have been assigned a particular purpose that interacts with a particular piece of hardware. So the memory registers live at the very end of the memory, like all the way up until the end. There's a tiny amount of them. There's about 50 addresses that are reserved. Some examples include like register LCDC. So this is a register in memory to control the LCD screen on the Game Boy. So you can do things like turning off the screen, enabling background images, enabling sprites, disabling them, and such. You got like timer, so that's the internal clock in the Game Boy. So you can do things like timers. SCY and SCX are what you'll see in a few slides are the viewports, so you can actually control the viewport in the Game Boy. And then like enabling interrupts as well. Oh, hang on, I skipped a... Okay, sorry, that slide wasn't supposed to be there. So the way it works is that the program would write to a specific address in memory, and then the hardware component will just keep continuously reading that address. So if I wanted to, let's say, make a sound in my game, you would write to a register called noise register 10, which has a specific address, and then the sound hardware will just keep reading that piece of memory over and over and over, and then that's how you make a sound. So we have the picture processing unit. So the picture processing unit chip is equivalent to today's graphics processing unit. It renders an area of 255 pixels by 255 pixels, but the screen will only display 160 by 144 pixels. It only displays 4 shades of gray, or in this case, 4 shades of terrible green. It has a 60 hertz refresh rate, or 60 frames per second. It only has 8 kilobytes of memory, which is not a lot at all, but you'll see how the picture processing unit works around that limitation. And the picture processing unit actually emulates the behavior of a CRT screen. Instead of drawing the entire frame 60 times per second, it will actually draw each individual horizontal line on the screen, and then when it finishes, it will start again, just writing each individual horizontal line. And it'll do that process 60 times per second. So the job of the picture processing unit is to take the data inside video memory, specifically the video memory, read the video memory. It'll read what's called the sprite table, or the object attribute map, which we'll talk about later on, and then interprets all that data into a signal that is then displayed on screen. So the Game Boy will draw 3 different types of things onto the screen. Each has different sets of behavior. The first one is background, which is typically used to draw the world, which sits at the very back of everything else. So everything else will be drawn on top of the background. The second are objects, also known as sprites. They're typically interactable objects in game, things like characters, items, coins, etc. They move independently of the background. So using what's called the object attribute map, we can actually specifically place the sprite in an area on the screen, and then also move the background as well independently. Lastly, windows. They're quite similar to backgrounds, but I can actually draw them in a specific region on the screen, and they can also be fixed in a specific region as well. So they're used for things like menus and such. The picture processing unit has no instructions like the CPU. Instead, it operates as a self-contained unit with minimal interaction. As I said before, the picture processing unit works by drawing the game over the display line by line continuously. When it reaches the last line, it will start that process again. When it's drawing the lines on display, it enters into 4 distinct modes of operation. These modes are the ohm read. So this is where it's reading the object attribute map. So this is where it's actually calculating what sprites need to be drawn on the current line it's rendering and where, and if it does. During this time, you can't update the video memory because the picture processing unit is reading all that data and processing it. And Nintendo strictly enforces that rule. So you won't see a game where it's actually updating the video memory when it's actually reading that same data. You have video RAM read. So this is where it's actually reading things like the background and the windows. Again, you can't update the video memory because the picture processing unit is currently processing that data. So the horizontal blank, so this is when the picture processing unit has finished reading a line and finished drawing that line, and it's preparing itself to read the next line. You're free to update video memory or sprites as you need. And then we have vertical blank. This is where the picture processing unit has finished rendering all lines and is preparing to start rendering the first line again. And then like the CPU, each mode takes a particular amount of time to complete as well. So things like the object attribute read mode takes 80 cycles, and these are CPU cycles. So this is how it figures out how to time itself. So it just takes the cycles from the CPU. And then things like vertical blank takes 4,560 cycles to complete. I'm not going to show you too much about the picture processing unit. It's a bit of a complex machine, but what I will show you instead is how it kind of fires off those modes. So it has a tick just like the CPU. It will take the cycles from the CPU and actually accumulate them, and then on whichever mode it's currently on, and once it exceeds that time, it will then fire off that event. So once it exceeds 4,560 cycles, it will fire off the video RAM read mode. So as I said before, the picture processing unit renders an area 255 pixels by 255, but the screen will only display 160 by 144. Here's an example here. So this is pretty much done to create the illusion of moving. So like here's Super Mario. Nope. So the viewport is the box that you see moving, and then you'll see how the Game Boy is actually also updating the world just before the character hits that part. So that box is controlled by two registers that are in memory, the SCX and the XCY mode. So due to the limitations of the available memory in the Game Boy, the device does not have the capability to hold a frame buffer, which is what most modern devices do, which is where you store in the individual pixels that are then taken and then just rendered on display. Instead, it employs what's called a tile system. So if you look at a Game Boy game and lay a grid over it, you'll see that a lot of the tiles look quite the same. A lot of these cells look quite the same. So if you look at like the floor, the books, the bookshelves, the wallpaper, and etc., you'll see that they're actually on repeat. And that's because that's done on purpose. So the Game Boy has a data structure for a reusable set of pixels called a tile. So a tile is an 8 by 8 set of pixels. It renders 32 by 32 tiles, but only 20 by 16 set of tiles are displayed. They're reusable, so you can actually use it more than once on a per screen. They take up 16 bytes each. Each pixel in the tile takes up 2 bits, and you can have 4 colors like white, light gray, dark gray, black. And so the pixel data for this tile is that binary. So like white is 0, 0, black is 1, 1, dark gray is 1, 0, and light gray is 0, 1. So here's the tile system. So here's the tile system in action. So these are the tiles that are in memory, and then this is what the user sees on screen. So you can see them being hot loaded in and out. So they're being read and being put into memory, taken out of memory when they're not needed. So that's Pokemon Red. This is Zelda. You'll notice that some of these tiles won't actually ever be displayed. Sometimes they're just loaded in with a specific function called a direct memory access, which is where it's a function in the Game Boy to load a huge amount of video memory with very cheap amount of time taken. So that's Zelda. So once we have all these tiles loaded in memory, how do we display them on screen? The Game Boy has what's called a map. So a map pretty much takes references to each tile and where you want to put them on display. So where you want to put them on the screen. They're used just for backgrounds and windows. You'll see how sprites work in a second. So I have a simple map here with a simple pattern. So what the map does is that instead of giving the actual pixel data, you actually just give it a reference to, the tile data, not the actual pixels. And so that way you can reuse them. You can assign where you want to show them on screen. And you save a whole bunch of memory doing so as well. So you can just see, I've only got 3 actual tiles with data, and the rest are just references to those tiles. So this is the actual map. You saw this before with Mario. Keynote is terrible. So the map is actually what is being displayed on the screen, but then only a chunk of that is actually being displayed, which is the square box. So that square box, which is the viewport, can actually overflow when it actually reaches the end of the right or the top or the bottom. So that's Pokemon. Windows works much the same way. Windows has their own map, and it also shares the same tile data with the background as well. Lastly is the object attribute map. So this is the table that actually tells the Game Boy where you want to show the sprite, what sprite you want to show. The object attribute map lives in the same area with like the hardware memory and the I/O. You've got attributes such as position X, position Y, tile number, priority, flip X, like if you want to flip it on the X-axis or the Y-axis. Lastly, we have the cartridge. So this is terrible. Lastly, we have the cartridge. So this is the actual, this is the bit that the component that holds the game. So you buy them in retail stores and you just insert it into the back of the Game Boy. There's 29 different types of cartridges. They can go up to 2 megabytes. So like games such as like Pokemon, where they're really big games, take up like 2 megs. They have up to 32 kilobytes of external storage. They support external hardware like real-time clocks and external storage as well. They're controlled by a memory bank controller, which is sort of like very similar to the memory bank controller as well. Control the memory. Yeah. So the Game Boy program lives in the space reserved for the game in memory. But as you probably may have already realized, is that the Game Boy only has 64 kilobytes of RAM. But if you have a Game Boy game such as Pokemon Red, which takes up 2 megabytes, you can't fit it in. So how does it actually read 2 megabyte game with only 64 kilobytes of address space? So if you take a Game Boy game and lay it out on a line and then chunk it up into 16 kilobytes, and then assign each chunk with a unique index, and then if we look at the game program, and then what you'll see is that so the first 4,000 hexadecimal 4,000 addresses are mapped to bank 0, but then we can actually hop swap any other bank in between the region of 4,000 hexadecimal 4001 to hexadecimal 8,000. And so this works. This works with another register, memory register. And so using the cartridge, I can actually tell the cartridge to read a specific region of the game and then load that into memory. So this is called the memory bank system. So when the Game Boy first starts, bank 0 is mapped to the first half, and then bank 1 is mapped to the second half. But then I can tell the cartridge to load in bank 14 between hexadecimal 4001 to hexadecimal 8000. To implement the cartridge, it's kind of built up into 2 different parts. One is is a class that implements the square brackets. The other one is the actual memory bank control, so the cartridge bank controller. Inside the actual game, it declares what's called the cartridge type. There's about 8 different cartridge types, and then I simply delegate the square brackets to the actual cartridge type, and then that will implement the actual banking system. So yeah, there's a specific region in the Game Boy game that actually declares what cartridge type it is, and then we just build up different implementations of that cartridge type. And then the actual implementation will then be in charge of that banking. I'm just being conscious of how much time I have left, sorry. So yeah, we have to manipulate memory in the actual memory in the cartridge controller because we have to read from the correct region in the game when given a specific address. And then once we have that, we can actually update the memory management units. So it will actually instantiate a cartridge. And then we can update the reading and the writing of the memory management unit to just read from the cartridge instead. Once we have all that, we create an emulator class. This will pretty much just encapsulate all the components, things like the CPU, the picture processing unit, the screen. I didn't talk about the screen, but the screen is basically just a simple C interface into the SDL library, which will just take the frame buffer that you saw in the picture processing unit and the memory management units. And then we define a method called run, which will just have a loop where it will take the CPU, the picture processing units, and then render the frame buffer to the screen if the picture processing unit will allow it. And then we just do emulator.new, take in the ROM, and then we just run it. Some of the things I didn't talk about, things like input controls, timer, interrupts, sound. There's a talk called the Ultimate Game Boy talk. It's an hour long, but if you want to know everything about the Game Boy, this talk will break it down for you. It's an excellent talk. I highly recommend it if you want to know more. If you're interested in the project and want to see the actual implementation of the emulator, it's up on GitHub at Colby Swandale /waterfowl. Thank you very much.